To another class with Ming. Today we talk about derivative. The derivative of a function y is represented using these two symbols, y dash, this is called y dash, or dy dx. Okay, and the second symbol is also read as the derivative of y with respect to x. And y dash of x, this is called y dash of x0, is the derivative of the function y at x equal to x0. Basically, this colloquially is the slope. I usually think of this as the slope at a point x equal to x0. So this is what I think of it when I see y dash of x0. And the other notation is written such: dy dx is equal to dy dx at x equal to x0. So this straight line here is read at x equal to x0. This is my point x0, y0. And here is the green line. The green line here is the tangent line to this particular point x0, y0. The red line is called the secant line. That is the gradient, or this is the line that connecting x0, y0 with another point xy. How can we approximate the tangent, the gradient of the tangent line? Well, we can do that allowing these 2 points to be closer together, so that the gradient, as you can see now, is approaching the gradient of the green tangent line. This is what we do. So let's say this is a blow-up version of what I'm doing. All right, and I'm going to call it this is my rise, and here is my run. Okay, my rise here is basically y of x minus y of x0. This is my rise. That's the increase. And if you let the run to be delta x, and delta x, let's say, can be replaced by another value called h, a symbol h. So then x can be replaced as x0 plus h. Therefore, the upper line here will be written as x0 plus h minus y of x0. So then the gradient of my red line, the red line is called the secant line. Right, this is called the secant line. So gradient of my secant line now is y of x0 plus h minus y of x0 divided by h. Derivative basically means this, that is, dy dx is the limit of this particular function. This is my gradient function. It's the limit of my gradient function as my delta x approaches 0. Or you can rewrite it as h approaches 0 if you wish. Find the derivative of 3x squared using the first principle. So we're going to write limit as h goes to 0 of 3x plus h, everything squared, minus 3 of x squared over h. And so this is the limit as h goes to 0. Now we expand the bracket, x squared plus 2xh plus h squared minus 3x squared over h. So now it's the limit as h goes to 0 of 3x squared plus 6xh plus 3h squared minus 3x squared over h. And now you can see from above that is the 3x squared and the minus 3x squared will cancel out. So we are left with this. And here you can see that the two terms in red have h as the common factor. So I can rewrite it as this divided by h. And h in the numerator and denominator cancel out. So we are left with 6x plus 3h. And here I have the limit of a sum. The limit of a sum is the sum of the limits, like this. It's a 0 here. And limit as h goes to 0 for 3h. The second term, as h goes to 0, will approaches 0, so that goes to 0. And the limit of h approaches 0 for 6x, well, x and h are independent to each other, therefore nothing will happen and it will remain at 6x. So the answer to this is 6x. That is, if your derivative is 3x squared, then, if the function is 3x squared, then the derivative of that function 3x squared is just going to be 6x. Check your answer. Welcome back. Here's the answer. I'll start with using the first principle, that is limit as h goes to 0 for x plus h, everything squared minus x squared over h. And then doing the expansion, just like before, you can see that x squared and negative x squared will cancel out. So you're left with 2x with this. The purple thing cancel out. The only thing left is blue. And then within the blue, the h is a common factor. So you're left with 2x plus h. And then, as usual, the limit of a sum is sum of the limits. I have 3x squared, I get 6x. Now I have x squared, I get 2x. Can you see a pattern?